Going to do essentially is first talking about inclusion polymorphism, going through some technical stuff about it, quickly through some examples that you have in the notes. Then afterwards, we're going to do a quick review on OOP345 templates, function templates, and how to specialize them. Then after that, we are going to actually show you how to do class templates, to create class templates. If you were my OOP345 student last semester, when the OOP345 class came up and I said, it was the end of the semester, and I said, this is going to help you in 345. That's what I'm talking about. So we're going to go through class template creations and understand what they are and how they work. After that, we're going to talk about relationships, association, we are going to talk about relationships, which is association, aggregation, and composition. Understand how they are and what do they work. Then I'm going to give you a code that I have written a few years ago. It's a good example of a kind of complicated C++ code. It's not that complicated, but the fact that I actually coded a manipulator. You know what a manipulator is, right? Like in C++, you can actually put stuff halfway through insertion operator and manipulates the output. So I have written them in a manipulator, and you're going to see how it's written. And also, we are going to talk about stack to understand what kind of composition is a stack and what is a stack. You're going to see that. You're going to go through those type of constructs when you take DSA subject, data structures. Well, for now, we are dealing with those. And we will start in exactly 1 minute, less than 1 minute actually. And we're going to need this. I don't know if I'm going to use this or not, but I'm going to pass it through anyway, just in case. If I have a question, then I can actually, especially for you. In case there's a question to be asked, that's what we are going to go through. All right. So today we are going to go through series of concepts back to back and understand how they work and what they are. Be aware that next week we're going to have a quiz on whatever we studied from the beginning of the semester till the end of this week's lecture. I strongly suggest to listen and watch the recordings of the next class, which is NDD, because they have 2 sessions. So what you are doing today, I'm going to do it in 2 sessions for them. So it's more in detail. So watch their recordings in case something extra is mentioned over there. The very first thing that I'm going to go through is inclusion polymorphism. And anybody remembers what inclusion polymorphism was from OOP345? Well, we said inclusion. We had 4 different types of polymorphism, the 2 major types. We had ad hoc and, anybody remembers? And universal. And we said ad hoc is casting and overloading, which is kind of fake polymorphism, because when you look at them closely, there is no polymorphism. It's just language faking it. And then we went to universal one, where we actually had inclusion polymorphism, parametric ones. And parametric one was creating templates, and inclusion was virtual functions throughout the hierarchy of the classes. So today we're going to actually take a look at that a little bit. So essentially, what I have today is this, and I see that that's not shared. Now it's shared. Okay. So what we have over here is this. I have a shape class. This is what you have in your notes. So I just brought it over here. I don't know if I added anything to it or not, but it's actually a working version of that. So we have an interface called shape. Anybody remembers what an interface was? Milady, do you remember what interface was? If you have to, again, remember the rule because we are in rush today. Either you answer or you simply pass it to the next person, okay? Quickly, okay. Okay. She chose the easy path. Okay, interface. Anybody remembers interface? Interface? Okay, shame on you all. Okay, interface was a class that had pure virtual functions all the way through. A pure virtual function was a function that was just a prototype equal to 0, which means it's a wish list for the children to have. A pure virtual function creates an abstract base class. An abstract base class cannot get instantiated. It's just an idea. And when you have an abstract base class with full pure virtual functions, nothing but pure virtual functions, then it becomes an interface. And please do not smile at your screen. Next time I see that, everybody's going to lose their computers. Remember that? Okay. All right, so shape is that. When I take a look at shape, in shape, I actually create a class like this. Each shape has an area that it covers, so essentially I'm going to say it returns a double area that is constant, cannot change the content of the class shape, and it's obviously a pure virtual function. A shape should be able to be comparable to another shape to see if they are the same or not. And a shape should be able to display itself. A shape is supposed to be able to clone itself. Now, what is clone? Clone essentially is a method that you add to a class, and that method creates a dynamic copy of itself and returns it. Okay? So it's kind of a copy procedure that is happening. But it's not copy, it's instantiation. So if you have a class and you want an identical dynamic version of this class, instead of creating a pointer and copying it and putting in yada, 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 you simply call the clone method of the class. And the clone method inside itself, copies the current one, copies target of this, and then returns that. We call that clone. So it wants to clone itself, and obviously we need to have a virtual destructor for all our classes, and because this virtual destructor of ours belongs to a template, an interface, I can simply set it to default, which means just create an empty one. So the old version of C++ was this. Oh, shoot, I hate this automatic thing that they do when you highlight something. Okay, there you go. So there you go. So when you do like this, that means an empty destructor, right? It does nothing. You can always do this instead. Said, hey, I want to have a default destructor, which means it's going to create it for you as if it doesn't exist. Then I have, for some reason it's wiggly, it's not supposed to. I have over here an insertion operator overload for shape. So any shape can be inserted into OStream. And that's the only reason I have a shape.cpp over here. The shape.cpp of mine only holds that aspect of the story. It's got nothing to do with what we have to do with shape. It's just what the overload of the shape is supposed to. So if I want to actually inherit this thing into, say, a square, what I need to do is to essentially create everything that the wish list of a shape is adding at least, or may add something more. I'm not going to add anything more to it. I'm just going to implement everything that the interface is instructing me to do so. And how does it instruct me? By creating a pure virtual method, I'm essentially saying if you want to exist, too many parameters for this operator function. I don't know why it's giving me this error message. It's absurd, but I'm just compiling it to see if I made a boo-boo somewhere. No, It's just intelligence going bananas. Okay. So as I was saying, the wish list that I have over here instructs me I have to implement any of these if I want my class to physically take a form. If I have pure virtual functions, the pure virtual functions dictates that the object, the class cannot get instantiated. And therefore, I did that. I created my class, which is a shape, which is essentially a shape. A square is a shape that has a side, and it has a constructor with a side. It can return its area. And obviously, we know how it calculates its area. Let me just close this thing and go to a square.cpp. So in square.cpp, I'm going to say the area is side multiplied by itself. We know that. And if I want to return a clone of myself, all I need to do is to create a dynamic copy of myself and return it. And that's clone. Anybody have any question about clone over here? You're good about clone, right? Very straightforward. I simply create a dynamic copy of myself, and I return it out. It's a copy constructor that I'm calling. Okay? And to display myself, I set it up, and I'm going to display the square where I find a square is supposed to show itself. The only thing that is over here and kind of needs a little bit of focus on is the equality operator over here. I want to check to see if I am equal to another shape. The problem is that what the parent is dictating to me is for me to receive a reference of a shape. And because I'm receiving a reference of a shape, I have absolutely no idea what the shape is going to be able to compare it to myself. What if the shape that is coming in is a triangle? What if the shape that is coming in is a pentagon? What is the shape that is coming in is a circle? Because I don't know what type of a shape is coming in, I have to upcast it to the type that I am before I can do the comparison. And that's where that constraint cast from OOP345, remember? That's where dynamic cast is coming from. So I'm saying dynamically, first I create a pointer because dynamic cast only work for pointers, not references. Then at first I'm going to actually create in a square pointer, I'm going to say cast the address of the shape that is coming in to a constant square pointer. Now, if the shape that is coming in is a square, the cast will be successful, and I'm going to receive a pointer of type square that points to that shape. If the shape that is coming in is not a square, the dynamic cast will return a null. So I know it's not a square anymore. Therefore, in my return statement, I'm saying, is the SPTR, the square pointer, null? If it is null, it automatically returns false, because null is false, goes to the end of the trinary operator, right? And if that's true, now I can say if the absolute value of the side of my square with the side of the other one, reduced by the side of the other one, is less than that precision, then they are the same, because they are doubles. You can never compare doubles. Doubles, you know, as I mentioned, if you have perfect logic that brings two double values to the value 2, it's very possible that an if statement between the two values go false, because one of them is 1.99999999999, and the other one is 2.0. To the eyes of the computer, those two values are not equal. But for us, they're equal values. Therefore, you can never compare two double values by equality. You have to reduce, find the difference, and make sure it's below the precision that you want. So if the difference between these two is less than 0.00001, it means they're equal to me. Are we good? And therefore, that is happening. So now, as you see, everything is fine and dandy over here for me, and I can actually work with this. I do the exact same thing over here for circle. So when you look at the circle, circle is actually implementing the same thing. If I look at circle.cpp, I will see that circle has a radius, not a size, and the area of the circle is calculated via pi multiplied by square radius by radius, right? Radius to power 2. And to compare the two, I do the same logic that I have done for a square, but I'm going to do it to a circle. So I'm going to say, now let's make this thing actually, because I just copied the code. So that's CPTR actually. Okay? So now I'm saying I have a pointer called CPTR. I do a dynamic cast of the shape that is coming in. And if that shape is actually a circle, then I'm going to get an actual address of it. If it's not, I'm going to know. And therefore, I can check to see if the radius of the two have the thing. And everything works perfectly. Why? Because a circle doesn't have a side. It has a radius. Then there is no property to check it. Check like that. For the rest of the stuff, it happens almost the same way. So if I want to clone, I simply say copy a circle and send out. And and to display, I'm going to have specific precision and show the display the way it's supposed to be. Now, if I actually go to my main, I can actually write a code like this. So I can create a code having a pointer to a shape. So essentially, make shape of mine will create a shape on the fly based on user's decision. So that says I have the character and double, those are the values that I'm going to get to be able to make the square. Then I'm going to say, if you want a square, give me an S. If you want a circle, give me a C. If it's an S, I'm going to get a double value for the side and create a new square and return it. Otherwise, I'm going to create a new circle and return it. Therefore, and because the return value is both shape, I'm good to go. So make shape will actually make a shape for me. Now, the cool thing is that because I'm doing that, I can actually say display shape, and the display shape of mine simply receives a shape pointer and displays it. As simple as that. No problem. Because of inclusion polymorphism, which is virtuality, when I call the insertion operator, the insertion operator goes to a shape, calls the display, and because display is virtual, the proper version of the display will be called at end. So, and I can simply clone it. Again, it doesn't matter what type of clone I'm calling. I'm going to say shape, clone yourself. So it goes to the shape. It wants to call the clone. Clone is pure virtual, therefore it calls the clone of the appropriate object, whatever the object is. If the shape is holding a circle, the clone of a circle will be called, and so on and so forth. So now that I have over here a CL that is a clone over here, now how can I actually identify what is equal to what? I'm going to go through the code, and we'll see the execution. So first, let's see what the code is doing. The code creates two shapes and clones one of them, then displays the two shapes that are received. Then it clones one of them, as we mentioned, displays the clone. Then compares the two shapes the user actually entered. Okay? If the two are the same shapes, it's going to say same shapes. Okay? If they are not, it's going to say different. And it doesn't matter. Different means two squares with different size or a square and a circle. To its eyes, they are different. And obviously, always a clone of an object is the same as its one. So this one will never happen. And at the end, I'm going to delete everything. And because in shape, I created a pure virtual I created a virtual destructor, it's guaranteed that I'm not going to have any memory leak, and the children will delete themselves properly. Running the code will do this. Square it. So I'm going to say I'm going to have a square over here. The length is 1, 2, 3, 4. That's the square. What is this? And now I'm going to have a circle. I'm going to put 1, 2.34 the same. Because they are not the same, it's going to say S1 and S2 are different. Now I'm going to do and obviously S1 and its clone are the same. I'm going to run it again. And this, I'm going to walk through it, don't worry. And this time I'm going to say square, 12.34, and square again, 12.34. And now, as you see, S1 and S2 are same shapes. Okay? So So a quick walkthrough to see how this works. Again, with Visual C++, F10 starts up the debugging and starts go to the first one. If I press F10, it runs the whole thing as one statement, which means it jumps to line 40, executing the whole thing. If I press F11, it goes into. If you don't remember what they are all mentioned over here. Step into, step over, step out. So I'm going to step into make shape. It goes into make shape. The return will be obviously null through the universal type of initialization. I set it to null. Character null, double null, everything. Then I'm going to ask if you want a square or a circle. I'm going to say circle, and I hit enter. It comes to switch statement, jumps to circle, and asks for the radius, and it's a double. I'll put 12.34. Then, because I put that one, it creates a new circle out of it. So I'm going to go to F11. It goes to the constructor of the circle, and therefore the circle gets created, and the return value is essentially address of a circle, which goes to the shape that is S1. This one, I'm going to jump over it. So now if I actually run this, it runs the same thing. Now I'm going to put another circle over here, and I'm going to put 12.34, exactly the same thing, and I hit enter. The very first thing it does, it calls the clone of S1. S1 is a shape. We know that. Because the clone is clone of a circle, it's going to go to the circle's clone. Therefore, it creates a circle and returns it out. Therefore, CL is 12.34. S1 is the same. It displays the first shape and the second shape, both circles, and displays the clone, oops, and runs everything. Sorry, I don't know what did I do, but I'm going to go on. Where did I go? Run it one more time. Yes, so I was saying that was circle 12.34. The other one is 12.342. Oh, C 12.34. Okay, and the clone displays itself. Huh. For some reason it runs through. It doesn't let me go through. I don't know why. Anyways, it's working properly. So it shows they are the same, and the two are identical. If I want to see how the dynamic cast works over here, I stop sign into the dynamic cast, which is, say, in circle. And I'm going to put one in square, so whichever is called. It's going to start right there. Now this time I'm going to actually make them different. So I'm going to press F5, and I'm going to go S34, C 12.34. So when it comes to the comparison over here, it is trying to cast the address of the circle to a square. Because it is not, it bypasses, and as you see, the pointer becomes null. Because it's null, false is returned, and therefore it's going to say they are different objects. But obviously the clones are always the same. And when it comes over here, now it's actually upcasting the circle to the square to a square. And obviously the answer is true, and it's going to return this value, which is a true value. And therefore it's going to say obviously the same. And deletes every single one of them, and that's that. So that was inclusive polymorphism, and that's that. Questions? All right. We good? All right. Now, a quick review of templates. So I'm going to go back. As you see, we have several different projects in the solution for today's lecture. Close all tabs. And I'm going to now set the main one as startup project. So this one is the one that I'm going to work with now. Okay, let me run it, make sure it's good. There we go. All right, first thing first. Function templates. We have done function templates in OOP345NEE, and the function templates we have done were like this. Essentially, we said we can create a template by writing the function, putting space holders for the types we want to change, and the template is never created. The code is not produced by the compiler unless it's called. So now if I run the program, a function, a binary version of the function logic will not exist in my executable. Running this will do nothing because it's not actually requested. But as soon as I actually attempt to call the function, this is what happens when I, for example, have two doubles over here, A and B, and I call the swap. Because this is a double pointer, and this is a double pointer too, and it looks at swap, it comes over here, takes a look at swap, and says, yes, it's the same function. Do I have proper typesetting over here to convert it to what it requests? Yes, it's double. So at compile time, it generates a function for me, literally. Generates a binary function for me called swap with a double pointer A, double pointer B, and this C over here becomes a double. And therefore the swapping will happen. And does the same thing over here for characters. I have two characters. As soon as I say address of A and address of D and address of E, because these are character pointers, it generates another one. So essentially, two versions of the template will get created automatically for me. This was called parametric polymorphism. This is absolute polymorphism. Why? Because the definition of the function ceases to exist if you don't use it. But as soon as you use it, a new one will be generated for you automatically. We good with this? This was OOP345NEE. Run it, make sure it runs. So, OOP345NEE function template. Now, say I have a function template. Let me remove these. Say I have a template to find the largest of two objects. So essentially, this is my template. It's a very costly template because it calls the copy constructor. So if I want to document this template, I have to mention the copy construction must be supported by the type because it's being passed by value, and also the operator should have been implemented by the type for it to work. So essentially, it's going to return the largest, a copy of the largest of the two back to me. So, for example, if I have actually, I shouldn't have deleted that one. I'm going to write over here A. I can say C is set to largest of A and B. Obviously, the outcome of this code will be 20 and C will be set to 20. Are we okay with this? Any problem with this? No. Now, let's say I have a structure or a class called container. And container has a Boolean method called has more. Okay? So essentially it does this. Return value greater than that's my class. If I have something like this, then how can my largest work for this? My largest template. It cannot. Copy construction, there's no problem because there are no resources for the, that class doesn't have any resources out of the scope, so that thing works. But that largest thing is not going to work with that container. So for that, I have two choices. Either I can overload the function largest and literally write an overload for it, which defies the whole purpose of the template. Because overloads get compiled and the code will exist in your executable, you use it or not. I don't want that. I want my largest template to only be generated if I use it. So how can I create a specialized version of largest only for the containers of container objects? How can I do that? For that, the syntax was to create a template and put an empty thing over there to say, hey, this template is a specialized one. It's not for any type. It's only for one type. That's why I'm not writing the name. That only means what's coming is a template. That's all. Then I write over here what it needs to be. So if I want the largest to work for those two things, I have to write over here container, largest, and then at right side, I write container, C1, container, C2, and in my return I say C1 dot large has more C2, and return that one. Okay, there's only one problem with this. Why is it giving me an error? Because that's capital. And why is this giving me an error? Oh. What did I do? Sorry about that. C1 and then C2. Sorry. C2. Okay, that's better. Are we okay? So the problem is this is not complete because this is just an overload. If I remove this, this is just an overload. I don't want it to be an overload. I want it to be a template for a specific thing. To actually create a template, specialized template call, what you need to do, you need to put the name of the type right after the name of the function name. So in here you have to mention container. Now it becomes a specialization. So that's the key. How do you specialize a function template? First, you overload it, as if you want to write an overload to work with that thing. Then you put a template with no type in front, and you specialize it by adding the type after the name. So now the compiler knows this function should not get generated unless a largest container thingy is actually created. Not only that, you can do it for anything else. For example, if I want to find the largest of two strings and return that one in a pointer, what if I want to do that? That's another way of doing it. So now, if it's constant character pointer, the largest is going to be passed between the two. So that's how specialization happens for functions. What you do, you overload your function the way you want it to be done. You put a template, empty template beforehand, and then you write after the name of the function what type of thing it is supposed to be. Okay? You good? Okay, now where it comes from? It comes from where you can actually specifically ask the compiler to generate a specific type of function for you. For example, if I have something like this, then the largest gets confused, right? I'm passing a double in an integer. It doesn't know how to deal with it. But I'm okay with that double to use its partial and just become 20. Or, no, I don't want that. Maybe I have this. I'm going to say, okay, I want that integer to be casted to a double. If you do that, you can specifically tell to the compiler, hey, ignore what you see as an argument, generate this for me. So that is a specialized call to a function template asking the compiler to generate that one for you regardless of what the arguments are. So you're essentially at line 33, you're saying, the heck with the arguments, generate largest for doubles, and then call it. And because it's a double, coercion will happen over here, which is essentially A being casted to a double and passed to a function, and it will be called, and there is no problem. So this is resolving conflict when your function templates don't know how to cast their arguments. Are we good? For those who are not asleep, are we good? All right. Okay. So that's function specialization. So I'm just going to put this one over here. I think I created another code for resolving, and I thought I'm going to bring that one up. Let me just save. So this is that's specialization. And this is the one that I was talking. So in here, as you see, I resolve it to an integer. I did it that way. Okay? So that's that. Resolving func template conflict. Pardon me? You're talking about this one? Yeah. Whenever the arguments are not set for the compiler to be able to generate what you want to generate. Because B and C are not of the same type, compiler doesn't know how to handle it because these two are the same type. Then you tell, yeah, you're telling the compiler, the heck with it, don't look at the arguments, create the largest so both arguments are integers, and then call the function. And because they are both integers, then this double will be casted to an integer and passed to it, and the function will run. So essentially, you are forcing the compiler to run the specific version of it. You good? All right. So that's that. Now, this was the easy part. Let's get a little more technical. Set as startup project. Okay. Back to OOP345. Back to OOP345. In OOP244, a long time ago, in a galaxy far, far away, we created a class using dynamic memory allocation, constructors, copy constructors, operator overload and stuff like that to simulate an integer array. We said integer arrays suck in C because they don't know what their size are. You cannot copy one to another. You have to write loops and stuff. We're sick and tired of it. Said, the heck with it. I'm going to create my own integer array. And that was the result. We said an integer array has an integer pointer, like all the arrays. But this one knows what it is size. Not only that, it can resize itself on the fly. And when you don't mention what is its size, it's going to set it to 1. And if you, let me just bring up the code for it too. Last row. And you see what it's written in here. Or it's too short, too small. Bigger, or it's good? It's good? Everyone, it's good? Back there, it's good? Okay, because I need lots of real estate for this. That's why I'm doing it. Okay, so when I create an integer, I'm going to say if size is less than 0, set it to 1. It means it's an array with 1. Then I do a dynamic memory allocation, set the size to the size that is coming in, and m data to the array that I have. Therefore, I have an array with whatever size I have. If they put 10 over there, m size will be 10. I have new 10 integers. M data will point to 10 integers, and voila, I have an array. Copy and assignment aside, we'll talk about it later. When it's deleted, it's going to remove the array when it goes off scope, so no memory leak. I can always see what is the size by calling the size method, size query. I can access access the elements using the index operator. So whatever index they put over there, if it's index less than 0, I'm going to say, I don't care about that. I'm going to make it 0. So if they put something negative, it's foolproof. If the index is greater than size, it means they went beyond. They had 10 integers, they went 12. If that's the case, I simply call the resize function, and I'm going to make the object bigger, as easy as that. And then after doing that, then I'm going to return it. So it doesn't matter if they go off the size, outside of the size of the array, it's going to resize it automatically. So the array was pretty intelligent. And if the array was being accessed as a constant reference, so you pass the array as a constant object to another one, then it cannot resize itself. Because of that, what I needed to do is to just prevent accessing other people's memory, so I just loop back on my own. So if they put something that is bigger than the size, I return the modulus. So say the size is 4, they return 5, they put 5, 5 mod 4 becomes 1, so it comes back in itself. Whatever value they put, it's going to be the remainder of it. So if they stay within the boundary, they're fine. If they go bigger, it's their loops back in, so it's safe. I even added a display, so if you display an array, it's going to show a comma separate. That's pretty unorthodox. An array doesn't do that, but I'm doing it with my array. The heck with it, it's mine. I can do whatever I want. So I'm going to say, if you want to display me, I'm going to show a comma separated value if you display the whole thing. And resize does the usual thing. It sets a new memory with the new size, copies all the old data to the new one, sets the size to the new size, deletes the old data, assumes the identity of the new one, and done. So that is resizing. These are all OOP244. And I also overload the insertion operator so I can just see out my entire array in whatever I want. Copy construction and assignment is obvious. I simply copy everything. So copy the data, and assignment the same thing. You know that. Go through it. We know exactly what it is. That's all OOP244. So if I want to actually test this, I can say new. I can add a source for it. So I'm going to say int array main.cpp. Sadly, I don't have the code for this. So I'm just going to create it over here like this quickly. Did I do namespaces for Seneca? Yes, I did. So in here, I have to say using namespace Seneca, which doesn't exist because I did not include the int array. Now I can say int array I4, and I can say for integer I set to 10, 0, I less than 4, and I plus plus. I can say I set to I plus 1. I'm just putting some values in there. Multiply by 10. And I'm going to say cout I. Okay? As simple as that. Run the program, and hopefully, if everything's okay. There you go. Whoa, what happened? Didn't work. Cout I. It printed the address? Int array.c. I don't have time for this. This is a reference of an array. O stream at left. Let me just check this first. Let's say 2. Just to show the integer. Now it's, okay, something is wrong in here. Oh! Can anybody tell me what did I do wrong? It looks like, take a look, let me just, that was a funny mistake. What did I do wrong? The problem is at line 6. Huh? Yeah, I meant, it's not an array. It's, thank you. It's a simulation. That's the size. It's an object. It's not an index, but I did it like that. So I made the boo-boo. Okay. So now if I run it, it's going to run properly this time. There we go. Okay? Thank you. Are we good? Okay. All right. That's why you prepare the code at home. All right. So that's that. So that we have done that. Life is beautiful. Everything's good. But that sucks because it's just integer. I want to have an array of anything. If I want to have an array of anything, I need to be able to convert this thing to a template. To convert the whole thing to a template. Okay. For this, I need to cover 2 rules. First of all, templates are essentially templates to build functions out of using the compiler, right? Literally templates. So for the compiler to be able to generate the code, it needs to have access to entire logic when it compiles it, right? Therefore, templates cannot have CPP files. Because if you only include the header file, when it compiles, it only sees the header file. It doesn't see the CPP file. That's why when you are creating a template for anything, functions, classes, or anything, the entire code should exist in a header file. You cannot have a template done in a CPP file. You good? Are we okay down to this point? So the very first thing I need to do to actually create a template thingy is to bring everything that I have inside a header file. So I'm going to create a header file. So add new item. and I'm going to call it dynamic array dot h. Okay, so it's dynamic array. It's not integer array anymore. Okay, a header file. So what do I need to do is essentially to create all the good stuff that I have for it. I've written it the whole thing. I don't want to put everything and kind of spoil the surprise. So I'm just writing it like this. Okay, so this is how I do it. The very first thing you do, you bring the whole thing. So that's the header file. I'm going to get the header file, copy, and put it at the top. Then I'm going to go to the CPP file, grab the entire function code, and paste it into the header file. Put it at the wrong place here. There we go. Okay? So now I remove this, and I'm going to remove these two. I'm not going to delete them so you can actually see it. Are we good? Are we okay down to this point? Number 2, we have to convert this to a template. So first of all, let's change all the names. It's integer array. I'm going to change that to dynamic array. That's what we want to change it to, right? Dynamic array. Is that the one? Dynamic array, yeah. So I'm going to say current document, change everything, poof. Now it's dynamic array. It's not integer array anymore. Okay, I have to save, because I see bug is happening inside my, something buggy is happening in here. I'm afraid it's going to crash, so I'm saving. When you see messages are not coming right on your Visual Studio, keep saving. Okay, so that's that. So first it's converted to dynamic. So I have everything as dynamic array. Okay, the next thing I need to do is to convert this to a template. How do I do that? A template only have overview on the scope that is coming after. So essentially, if I want to convert this class to a template, I have to write over here template, type name, what did I call it over there? T? I'm going to call it T. T, okay? So this becomes from line 7 to line 21. This covers that one. I'm going to copy that, and I'm going to add to this next one. This scope only has one line, so I have to do it like this. You see? Just for one line, I have to put the type name. Then I have a function over here. That needs another. This one needs another. This one needs another. And this one needs another. So type names will be added to the beginning of every single scope that I have. Functions, classes, whatever I have. Anything that you have that is related to your class must be templated. Even the helper function that you have. We go okay down to this point? That's step number 1. Step number 2 is to actually follow through 2 steps, and the second step has 3 parts. Number 1, you have to change the type, the type of the focus of the class to the templated T. So anything in here that is supposed to change to the type. So you want an array, right? So all the elements should change type. If it's an array of integers, this time it should be an array of classes, array of motorcycles, array of chairs, array of doubles, array of anything. So first, the elements should change. Size remains the same. 5 chairs, 5 human beings, 5 integers, 5 doubles. 5, they're all integers. I don't need to change it. Okay? So now I need to focus and start doing that one by one, which means I'm going to do it only for the class and one of the methods. Then I'm going to bring all the code that is done. and show it to you, okay? So now, for this one, obviously, the pointer needs to be a T, correct? A type. In here, int m size remain that one. New size remain that one. New size remain that one. Nothing over here. This is returning the size that's integer. This one is returning the element value. Therefore, it has to be T, because I'm returning the element. Okay? The index is index. This one, I'm returning a constant type. Again, it's the element. The rest remains the same. Voila, done. Okay? Are we okay down to this point? Are we okay? Number 2. When I wanted to specifically call a function template when the type was a mismatch, I put the type of the type I wanted to convert to in front of the name of the function. That's how we specialized it. Because classes don't have arguments, let me go to my main. I'm going to actually bring the main in. So remove. So because an array, look at line 20. An array doesn't have a type. It cannot recognize what you want. There is no prototype to tell what type you want. So when you are creating a class template, you are always specializing it. So I'm saying I want a dynamic array of type containers to get created. Because of that fact, every single class name in your template must be specialized by the type T that you are creating. So because of this fact, because I'm saying over here, I want a dynamic array of containers, then every single dynamic array that you have must carry the T with it, with few exceptions. So add the signature of the template to all the class names other than, first, the name of the class that comes right after. That won't get it, because it's just the class name. B, constructor names. Constructor names, we said they are special things. They are not actually name of the classes. You are telling what happens when the class is getting created. So it's not instantiation of a class. It's just identifying what is the constructor. Those don't get the signature. And another specialized one is the destructor. That one doesn't get it. Other than that, any class name that you have must carry that T thingy with it. Now, whatever you call it type, type goes over. If you write T, T goes over there. So this won't get it. This is a constructor, won't get it. This is a constructor, won't get it. This one is returning a reference of a dynamic array object. It must carry the T. This one is receiving the reference of a dynamic object. It must carry the T. Over here, we don't have anything else. That's it. Done. Now let's take a look at this one. This single line that I have one reference of dynamic array that goes through. That must receive a T. Let's look at the constructor. The name of the constructor won't change, but what it belongs to, that needs the T, because it's not the constructor. Size is size. Here I'm creating a new integer array. That's not the case. It has to be T array. And I continue with everything like that. Convert everything like that, and the final result will be something like this. As you see, every single thing is passed through, and all the flags are added, and now I have myself a class that doesn't exist unless you request for it. It will not be in your executable unless you request for it. So in here, I'm saying an array of containers, or I can say a dynamic array of doubles. Doesn't make any difference. Okay? So now if I do this, I'm going to make this one 3. Actually, 2. So that's an array of 2 doubles. But in here, I'm going to say di set to I plus 10.123. So that actually resizes the thing too. And I can say over here, cout, new version of cout. Now, as you see, I have 2 different arrays over here. And one is a double, the other is a container. And if I run the program, you'll see that it works for both of them. And I get an error. What is the error? What did I do wrong? Let me see first if I have stuff over here. Dynamic array, dynamic array, dynamic array is added. Why did I get assertion? Oh, no, C size, yeah. This is fine. Double. That's good, that's good. This is the first one going in, so it sets, it doesn't resize, set the index out, good, so this is good. This one is the same, should be good. 2. Now, this one is good. This one is size is 2, index is 2. It's going to resize to 3. It goes to resize. New size is like that. Creates an array of doubles. Copies all the old ones. And, oh, why is it deleting data twice? What the heck is that? Okay, I don't know why I have that thing over there twice. I think that was the reason. Let me run it. Did it run? There we go, there we go. So now it's fine. I don't know why I had that thing twice over there. Anyways, so there you go. Now I have an array of containers and doubles, and it works for everything. Class templates are like that. And this looks like a good thing to use, but you don't need to do that. I always mention this to, like, I don't think you're old enough to remember that Apple had this slogan that used to say, if you want to do this, there is an app for it. For anything they would say, there is an app for that. You want to do accounting? There's an app for it. You want to play it? There's an app for it. It was their thing that anything you want, there is an app for it. Anything you want to do with C++, there is an STL template for you, standard template library for you. You want an array? There is a template for an array. You want an efficient array? There is an efficient array called vector, and that's a cool one. So you can do anything you want in a standard template library, literally. Anything that you do in your life of programming in the next 5 years, there's an STL library for it. Either logic or containers. This is a container. But it's not only containers. Sometimes classes do things for you. You have a class that is a utility class to process things, to run stuff, to do things in parallel, things like that. There's always a standard template library for it, and we're going to learn and go through it as we're going to see how it happens. Are we okay with this? We're good? So these are essentially standard template libraries. And that's our break for 35 seconds. I'll sip of water, and then I'm going to continue. Don't go anywhere. If you want to have a sip of water or do something, do it. So those are class templates. And what am I going to cover after that? Sorry, I usually go by classes feedback, but this time I actually wrote over here what am I supposed to teach, not to forget. Now we're going to talk about relationships and show you some examples of it, and we're done. All right, relationships. I'm going to go back to the main lecture over here. Existing guide. No, set has start a project, and there we go. So, classes talk with each other. You know that, right? When you have a class and you pass another class to its methods, one class is sending a message to another class. You understand this, right? For example, you have an array. What is an array? Think about an array as a class. An array is essentially a collection of elements, correct? An array is a collection of elements, 0 to whatever it is. Are we good? Now imagine if an element is a class. Then essentially you're going to have, or house and its rooms. They are in relationship with each other. House is a class. It has some rooms. Teachers, students. We are classes. You are actually invoking my teaching method right now to teach you something. I'm returning information to you. We are communicating with each other, right? All these relationships fall in 3 different categories. Number 1 is association. Association is exactly what we are doing now. Teacher and a student. Teachers and students, they are in association with each other. I give you knowledge, you give me test result, I mark your test, I give you your mark back, and we pass information back and forth to each other. If I get hit by a truck and die, you guys are all healthy and good. You exist. There's nothing wrong with you. Another teacher is going to come. If all this class is canceled, I'm still a teacher. Nothing happens. So our classes don't have any ownership on each other. We exist separately without each other's existence. A student can still be a student if a professor doesn't exist. A professor is still a professor if there is no students. But of course, when we put these two together side by side, they can have one-to-one relationship, tutoring. They can have one-to-many relationship, which means one teacher teaches many students. We many-to-many relationships, like this semester, you have 2 profs. First half is me, next half. You follow what I'm doing? This is the definition of association. You okay with this? Okay, good. That's number 1. How can we actually implement such a thing? This is how. Take a look. I have a class student with name or whatever. Okay. Now, what do I have over here? And the student over here, and I have a teacher, and teacher has an array of students. Okay? It's very possible that you would have something like this over here too. Class, teacher. If you have only one teacher, depending on how you are designing this. Okay? I can have over here, what's going on? Somebody's screaming? Was it the scream that we should call security, or it's somebody's going bananas? Laughter? Oh, those guys are happy. Okay. Okay, teacher pointer, OOP345 teacher. Something like that. So a student can have a pointer of a teacher, okay? And a teacher can have a pointer of many students. Well, these are just pointers. When I actually add a student, all I'm doing, I'm getting the address of a student and I'm holding it. I'm not going to do anything to it. If I get destroyed, my array of pointers will go with me, and student objects still exist. And that is called association. We okay with this? Okay. The example that I'm giving you right now can be implemented in many different ways. Be aware of that. Okay? But the one that I'm doing is what we call aggregation. Aggregation is a little stronger than association. Say library and books. Library, I don't know, it's very distracting to me. I want to see if I can actually see them so I can screen back. Okay. All right. Anyways. Give them a dirty look like, what are you doing? Anyways, and they just laughed at me. Anyways, so teachers don't have those seriousness that they had before, right? Anyway, so a library and books. So essentially, when a library is built, it receives books and it receives copies of books and puts it in its bookshelf. Okay? So the relationship between a library and a book is that the books now belong to the library. They actually stamp it and everything, right? And if you tear down the library, the books go with it. But the copies of the book go with it, not the original book. The books can still exist out there. Someone else can have a copy. Burn down the library, which we never want to do. The books are gone with the copies are gone. This is aggregation. Aggregation means when you have relationship, the owner object, the container object, holds copies of things that it has out. It can modify it. It can do things with it. And when it's gone, it destroys them all. But what is being destroyed is copies of what we have outside. Okay? That we call aggregation. And this is how it's done. Now, I did kind of a super duper version of this thing, of library and books, and I'm going to show you. But this is essentially what it is. As you see, I have book, and book have titles, and still I have book pointers over here, as you see. But the difference over here is this line. You see that? Instead of just holding the addresses of the books that are out there, I'm creating copies of books, and I keep them. And if you look at my destructor, I'm going to actually go through the books and delete them when I'm gone. Does that make sense? So aggregation is kind of an ownership of copies of things out there. It's a little stronger than association. Of course, those copies can exist, so the objects can exist, they can belong to someone else. Still, another library can have copies of the books that I have with no problem. You good? That's aggregation. Yeah, there's, what do you mean the same? Look, I could. Two libraries can share a book. It's not that they have identical, exact same inventory, but they may have the same copy. It's a many-to-many relationship type of a thing, but an aggregation controls the existence of its members. When it's gone, all its members gets deleted with it. It keeps copies of its members. We okay with this? And the last one is what we call composition. Composition, the owner object is actually composed of its members. And the members actually give meaning to the composition. Composition and the members of it have a meaning outside of its composition. Take arrays and elements. Can I get an element out of an array? Say, this is an element? And it says, element of what? It needs to belong to an array to be an element. An array cannot be an array without its elements. And when you add a value to an array creates an element and keeps the value in it. So even the creation of the members are done by the composer. You are not allowed to create an element out there. So essentially, the composed material are usually fully private. Even their constructors are private. And that's where we have friendship, which essentially the composer becomes a friend of the composed element. You follow what I'm saying? That's why I always say, if you see anybody's creating a friend other than class friendship, it means there is a flaw in design. Methods are never supposed to be friends. The thing that you learned in OOP345, when you did the extension operator and you made it a friend of a class, absolutely wrong. Big no-no. It's like using go-to statements these days. It's horrible. You shouldn't do that. You're essentially giving the key of your class to a stranger. Things may happen outside of your control. You don't do that. Okay? So friendship is, I always give this example, and it's sad, but it's real. Okay? I have a dog. I love my dog. It's like my daughter. Okay? Like, I have a dog, and I'm my dog's friend. But I can take my dog to the vet and put it down tomorrow. That's the friendship in C++. Full ownership. You call it a friend. It's not a friend. You own the thing. Got it? Okay. How do we implement it? Perfect example for composition is house. House and its rooms. Take a look at the house. It's fully private. The constructor is private. You cannot instantiate it. And I have a forward declaration of house, and at the bottom I'm saying friend class house. This is the only time a friend is okay, and nowhere else. And now, when you are actually adding a room, as you see, you're just adding the name. You are not adding the room. You say, I want kitchen. Then the class will actually create a new room for you and put it in there. That room cannot get created outside. You cannot go to a street and go, oh, there's a room. It's impossible. The room is in something. It's in an apartment, in a building, somewhere. You don't have a standalone room. It doesn't make sense. And that's what a house is. It creates its elements and it destroys them, and the elements cannot exist outside of it. You cannot have a room outside of a house. It's stronger. So essentially, composition is a strong aggregation. Are we good? Questions? Suggestions? All right. Brings us to this. So I have to actually activate the camera, because it doesn't make sense if I keep talking about it but no one's seeing it. There we go. Okay. Wow, I can see myself up there. All right. So this is a stack of markers. Stack is such a thing. This is a stack of markers too. An empty one. I don't have any markers in here. The very first marker that I put in here is the black one. So the first one that goes in is black, right? The second one that I'm pushing in is blue. The third one that I'm pushing in is red. Now, if I want to pop one out, which one will come out? Black, blue, or red? Red. It's impossible to take the blue out. It's in the middle. I can only pop the top one, right? So you pop the last one. So the first one that goes in comes out last. That's first in, last out. And then the next, and pop, and I have empty. Are we good? This is a stack. This is a structure of a stack. Stack is one of the most important containers and constructs of computer science. If we did not have stack, a function call would have been impossible. Every single function call that you do, when you call a function, and at the end of the function you say return, how does it know where to return to? How can it remember where to return to? It's using a stack. So any function call is a push. So when you call a function, CPU looks at that point and sees where the function is being called. It pushes that address into a stack, and then it goes to the function. In that function, you call another function. That address will be pushed in another stack. And then it keeps going like that. The very first return that comes, it says return. Where to return? It pops the last one from the stack. So it knows where to return to. So the whole concept of calling and returning and calling and returning is done with a stack. And if you, by mistake, call a function in itself improperly, not recursively, incorrectly, if you call a function in itself, you will see that the program hangs a little, then it crashes with the message stack overflow, which means you kept pushing in the stack. You keep calling yourself, and you're pushing the addresses into the stack until the stack fills up all your memory, and there is no space. Okay? All right. So that's that. So this one was, let me just write this thing, composition. And the question for your quiz will be this. I'm going to tell you, there is this class, yada, 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 and this class, yada, yada, yada. This class is a composition of this class. Go, write the code for me. Okay, I'm going to say, I have a house and I have rooms. Create a composition for me. Okay? I have a book and I have pages. Create a composition for me. So you have to come up with a way to write a book and add a thing, and okay? So I'm going to tell you how a page can get created, and then you're going to create a book with pages. Something like that. So that's going to be your test. Okay? The concept, I'll do it in midterm. I'm not going to do any concept in any quizzes. You are just writing programs for me. But I'm going to tell you the details of the question, so you're going to know exactly what the topic of the question is, and you can study, and you can come for it. Next week, today, we have a quiz. Stack. That construct is surprisingly easy to create. Take a look. I have a template, class template called node. So an element of a stack, essentially, is called a node. And how does it work? How does it work? I wish I had a camera that I could actually point in different directions and I could show you, but I always do this, and so if you're not here, you can't see, but this is an in-person class, so I'm not to blame. Okay, if you're not here, it's your fault. Anyway, so this chair, as you see over here, is a stack of human beings. And how many people are here? No one. As soon as I come over here, I'll come over here with an index finger. And I'm showing the ceiling. So how many people are here? Only me, right? Point to the ceiling. How many people are now in the stack? 2, because I'm pointing to him, he's pointing to the ceiling. Point to the lady. And now we have 3. Now if I pull, the lady at the end that is pointing to the ceiling will come out, and now and this one. So that's how stacks work. Take a look at that. Look at my node over there. The node that you see, it has a node pointer called next. So essentially each node can point to the next. And the one whose next is null, that's the last one. That's the top one. And I always keep track of that one. Okay? Actually, the one that is, the next is null is the bottom one, sorry. The one that is in a stack, not a queue. There are 2 different things. But in a stack, the one whose next is null is the bottom one. Whoever is at the top is pointing to the next one, next one, next one, next one, and the top one is the one that is so it goes like that. So essentially, my example was wrong. So when I am right now at the top, and over here like that, when I point to him, go, now still I'm on top, now he's on top, and now point, and she's on top, okay? But the thing is that because actually she's at the bottom, not top. How do I explain it with this? Give me a second. Let me do it one more time. I'm pointing at Q. So I'm pushed in a stack, and I'm pointing at correct. And the next person, change seats. I can't do that. Because the seat is the top, I can't do that. Then he has to come to the seat, and the next person goes. So that was the wrong one to do. The reason it didn't work out, because the seat. So he should come over here and then point at me, and then and it keeps going to whoever is in a seat as at the top one. That's how the stack works over there. Now, how the stack is going to actually work is like this. Now I'm going to actually draw you the right one. Okay? This is how it works. There you go. Anyone have one of those pencils that has a thing that you can work on any cell phone with it, with the rubbery thing at the end, that you can draw on cell phones? No? I have to use my finger. Sorry. Okay, so this is what we have. So essentially, with a stack, you have a top. Okay? You can see it over there, right? And that top is empty. There is a pointer pointing to nothing. As soon as you add a node, the node comes in, and that node is pointing to nowhere. But the top is pointing to that. Follow? So this is top. Are we okay with this? Now if I want to actually add a new one, a new node is added, right? That node wants to go to top. So what it does, it points where the top points, and now top points to that one. So now if you follow the top, red was the last one, right? The top goes to that one, red, and red goes to green, and green goes to null. Now if I want to add a new one, it doesn't matter where it is. Wherever the top is pointing, it's going to point to that one. And now top is going to point to the new one. Now blue is the first one, and obviously this is gone and this is gone. Okay? Now top points to blue, and it goes like that. Are we okay up to this point? Now as soon as I want to extract the value of the top is pointing to what I want to point to, right? So all I need to do is to take the value out and make the top point to the next of what is currently the top one. You see this one. So all I need to do is extract it and make the top to point to the last one. Now I extract the red one and make that one point to the next one. Oh, the P of the top is gone. Now if I want to extract the last one, then the last one is going to be gone and the stack is over. So I do the same thing exactly over there with the node. If you look at the code over here, my stack, the class stack, has only one pointer that is called top. And whenever I push something into it, as you see, the constructor of node receives the data that it wants to keep and the address of the next one. So I simply say, push one new node in, put the data in it, and make it point to the top. After that, make the top point to that one. Therefore, anything that I'm pushing, top will always point to it, and it's going to point to the old top. And anytime you pop, it gets the value out first, remembers what to delete, makes the top point to the next one, and then deletes the current one, and done. And returns the value. And you can always check to see if your stack is empty or not with a top. And the destructor is simply keep popping until there's nothing in a stack. So your test, your task is to get one of those 4 colored pens on a piece of paper, walk through this code, and see how the stack works. Again, do you need to code this? No. The STL, we actually have a stack. You can create the stack. It's there, and it's run very efficiently and nicely. Good? Okay? But it's good thing to do. I had the code for the queue too, but I didn't bring it in. That becomes too complicated. So essentially, queue is this. With a queue, you have 1, 2, 3. One is the head. The other one is the current, and that one is the tail. Head, current, tail. And each node knows who's next and who's previous. Head always points to the beginning. Current points to the one you're dealing with now. Tail always points to the last one. And all these guys are aware who's next and who's previous. So this one knows this is next. This one knows this is next. And this one knows after me there is no one. This one knows who's previous. This one knows who's previous. And this one knows there is no one behind me. And that's a queue. That's actually a priority queue. Now, if you want to add something in, I'm going to draw it, confuse the heck out of you, but that's DSA. You go and learn it in the next semester, hopefully. So if I actually want to add a new node in here, all I need to do is to add the node, make this one point to the next, this one point to the last, this one point to here, and this one point to here, and remove these two. And I can add anything in the middle of the queue without shifting on anything. That's why these type of stuff are much more efficient than arrays when you want to insert something in the middle or end. You only add one thing. If you want to add 1 to the size of an array in dynamic memory allocation, what do you need to do? Build an entire array that is 1 element bigger, copy the entire thing to the other one, delete the old one. Holy mother. You know how many things you have to do? This one is just 1. So very simple and straightforward. These are all compositions, by the way. So we are done with this. Next is to show you the confusing library. And that, again, there is no need to understand it now. I'm going to tell you what it is and how it works. Go home and walk through it. Try to understand it. These walkthroughs teach you stuff, okay? So please do that. This is what my library looks like. Each element of my library is an IO-able thing, okay? And it has a title. They have a title, okay? Now, a library can have many books. A book can appear in many libraries. To be able to show the libraries, to be able to, so the dilemma happens over here. So if I create a many-to-many relationship between a library and a book, whenever I want to show the library, what's going to happen? It wants to show the books inside, correct? Now, whenever you want to show the book, it wants to show which library it's in, correct? That becomes an endless loop. So when I'm showing the library, it's going to show the book. Then the book is going to show the libraries that it's in. Then each library is going to show the books that it's in. Then the book is going to show it's going to be an endless number of prints. That's why I need a manipulator called hide subcontent. So whenever a library is printed, before printing the book, it tells the book, hide your subcontent. Don't show which libraries you're in. And therefore, when library is shown, it only shows the books. And when I show the book, when the book wants to show which libraries you can find it in, it tells the library, hold your subcontent. Don't show it all. That's the manipulator. So how does the manipulator work? Manipulator says, let me show you. Essentially sits in between of the extraction operator. You see that? That extraction operator makes the hide subcontent object to sit between printouts. Like cout. When you have cout, you put a width, and then after width, you show 55. And the width is 10, so it passes through width. So width prints the 55 in 10 spaces when you're using a manipulator. It's the same thing over here. So how did I implement this? IOable can display itself, read itself, and it can hide its subcontent. Obviously, it has a virtual destructor. It can be read or it can be printed on IOStream or OStream or from IOStream. Hide subcontent, which is a manipulator, what it does, it puts itself between an IOable object, and when it's there, it activates its hide. So essentially, calls the hide subcontent of the object. Therefore, if it passes through this, it's not going to show its subcontent. How do we actually make that thing work? We're going to make it the manipulator over here is what we call a singleton, which means I instantiate the hide subcontent inside the code of IOable, and I make that one available everywhere. Usually, these things have a private constructor. Okay? Well, we'll see. We'll talk about that later. A library is not copyable. It's not assignable. It can be checked to see if it's the same as the other library. You can add books to it. You can add books using insertion operator. You can hide this subcontent when it's displayed, or when you display, if hide subcontent is not on, it's going to display everything. And it works the exact same thing with the other one. So when you're actually looking at the code when it's actually running, this is how it works. I created library Vaughan, library Toronto, and Yorkdale, and few books. Then I create an array of pointers to hold the addresses of those so I can actually go through them and print them in a loop. Then I create a show function. What it does, it essentially prints a prompt, draws a line, and shows the content of what is being printed. and passes through them one by one. So essentially shows all the elements of the array. So I'm just passing these two. So to Vaughan Library, I can add books. To Toronto Library, I can add books. To Yorkdale Library, I can add books. Then, by doing that, this book remembers that is in the Vaughan Library and Yorkdale Library. This book remembers that it's in the Toronto Library and York Library. And when I show them, it shows it exactly that way. Okay? Your job is, again, to go through it and see how it works. So this code works as follows. I'll go through it I'll walk through it, but after you actually go through it. So when I run it, did I put it as a startup library? No, I didn't. Did I? No. What is this? Oh, this is Stack. I was showing employees. Sorry about that. Set as startup project. I don't think this runs on Matrix because I have this assignment over there. It's going to give you a warning. There you go. So as you see, first it shows the library and the book when there is nothing inserted in them. I printed everything. It just said Vaughan, Toronto, Yorkdale, over here the list. After I add it, now when I print Vaughan Library, it tells me the books available are these. When I print Toronto Library, it does the same thing. And when I'm printing the book, it tells me that this book is available in these libraries. This is a perfect example of an association or aggregation. And that's it. Please go through the code and see what is the complex code. I just want you to kind of warm up your muscles by going through it and see how it works. Okay? Most of the time, this is what you're 90% of the time when you start your work, if you are lucky and you're a good programmer, this is what you're going to do first, fixing other people's code. Okay? So to go through it and understand how a code works that you've never seen, that's the first one. Okay? Please go through it and try to understand it. You go through this. If you understand how it works, how this works, you're going to be good in this subject. Okay? And if not, then you come back and ask questions. Quite frankly, just a second. Every time that I do it, I've written this like, I don't know, 5 years ago. Every time that I want to teach it, I have to go through it and remember what I did, because I don't remember really how it works. Yes? Code been posted? Let me do it right now. And that's the end of today. So let me just save this. I'll close this. And 345NEE, commit. There you go. It should be all up there now. Okay? Have a beautiful day, everyone.